this a lot of information in this slide, but I'm interested here talking about the condenser. So let me summarize so far what we have done. This is the plant, the actual plant we are looking for, and we have seen the simple cycle, Rankine cycle, ideal simple cycle, which presents this one. So presented this in a simple ideal cycle. Then we made one modification here, which is the reheat cycle, where we added a reheat section here, and therefore we presented the boiler, and then the goes to the turbine, and then out of the turbine goes to reheat again, and then to another turbine. So this is one modification, which is the reheat cycle, and as we discussed, the objective of this reheat cycle is to improve the power. This is definitely the power will be improved. The issue of the efficiency, it depends here. What is the status of temperature 1 and 3? Are they close to each other? Then the efficiency will be improved. If not, the efficiency may be reduced. But the objective here of the heat cycle is to improve the power. Okay. Then I wanted to discuss something else here today, which is a condenser. This is one of the questions sometimes we ask. This is the condenser here, and in the condenser we cool the steam from out of the turbine and condense it. So this is here from 4 to 5 here it is condensed. How do we condense this? We take heat from that. How do we take the heat? We pass water in, and water comes out. So this is cool water, and this takes the heat from the steam. And this is either a cooling tower or ocean or a river or something like that. So I want to discuss the energy conservation for the condenser here. Okay, so this is the condenser, and to the question normally comes to be what is the amount of cooling water that we need to condense that. I need to take heat from the steam, need to condense it, and this heat will be taken by cooling water. So how much amount of cooling water we need here? And this is the condenser here. You have the water in, and the steam in here. The steam goes around in the shell here, around the tubes. The tubes come here, the water comes in these tubes, and then go out here as water out, and the steam comes here and leaves as condensate in this outlet here. And therefore, the energy, it's easy here to say that the mass of cooling water multiplied by H exit minus H inlet. It gains, this is the energy gained by the cooling water. This will be equal to m dot steam multiplied by the enthalpy, enthalpy difference, or the condensation in the condenser. So this is here is the mass of steam multiplied by delta H along this here. So in this case will be 4 minus 5, and then the water HE minus HE. Normally the students do this well, but here how do you get HE and HI? This is normally at 20 and this is 30, so you go to the table and get HF at those, or you can take C delta T here. So the question here is how much is the amount of cooling water? So this is normally a part of question we normally ask, and this is needed to have the design of the cooling tower here. Okay, any questions? Okay, if there's no questions, then I will go to the next modification. We made one modification here, which is the reheat. The other modification is what's called regenerative vapor power cycle. So we are going to consider another modification now. Let me say right now that the objective of this modification here is to improve the efficiency. So our objective is to improve the efficiency. So this is the objective of regenerative cycle. For the heat cycle was the objective of improving the power. Here we are going to improve the efficiency. And the power here may be reduced. However, when we combine both together, reheat and regeneration, then we are definitely sure that we are improving the efficiency and the power of the cycle, and therefore almost all thermal power plants will have both reheat and regeneration. So let us concentrate now on the regeneration and understand this. Okay, what happens here? Okay. So this is the cycle. Let me look at this here and see what is the, so let us see the original cycle. Out of the condenser, this is a simple cycle now. Out of the condenser, it goes to a pump, then to the boiler, then to the turbine, to the condenser. So this is the cycle here. Without this part, this is the part that we are adding today is this part here. So normally the cycle will go like that: out of the boiler to the turbine, condenser, pump, and then the boiler again. What we are going to do here is that we are going to, in the middle of the expansion here, we are going to extract, take some steam out from the turbine and use this steam for heating the water from the condenser. Okay, so now what we are going to do here is the objective is to heat the water before going to the boiler. Why are we doing this? Okay, why we want to increase the temperature of the water before going to the boiler. So the water comes here at state 4 from the condenser. In the simple cycle, we take it right away, pump it to the boiler. Now what we are going to do here is to heat it in the what we call feed water heater, and then pass it to the boiler. Let me first say feed water heater. What do you mean by feed water? Feed water is the food for the boiler. All right. Water is the food for the. In Arabic, we say here مياه التغذية. مياه التغذية means that the boiler eats the food for the boiler is water. So water goes in here and then it is fired and then go to the steaming. If there's no water in the boiler, it will fire. So you have fire here in the boiler, and therefore, if you do not provide water, then the tubes will fire. This is the example here. We have gases going inside this boiler, and then the gases will give heat to the water, and then the water will change to steam. So feed water, it is water going to the boiler. Why we call it feed water? Because this is the food for the boiler. And this is the first thing I wanted to say. I will put some scales of understanding why do we heat the water. Can anyone start discussing now? Why do we need to heat the water before going to the boiler? I'm
To
saying that
reduce.
this will improve the efficiency. The
Faisal,
objective
okay.
is to improve. How this will improve the efficiency? Can you say the name, please?
Faisal, okay.
What's the
Uh,
name again?
Faisal, okay.
Faisal. Okay, Faisal, go ahead. Yeah, I remember
Because
you mentioned this once before, right? Okay,
yes,
type.
because it will reduce the temperature at which we add heat to the feed water, so it will reduce the reversibility. The result of that, the efficiency will increase.
Okay, I think Faisal answered well, and then he deserves a bonus, inshallah. And then I just wanted to start. He went to the high level of discussion I'm talking to. Let me start first with the lowest level that anyone other than students at your state here can understand. Now let me ask you: when you get a sandwich from the freezer, do you eat it right away or do you heat it?
Hate it.
Why do you heat it?
Can't eat
So
it right away. It's very
you
cold.
cannot eat it as cold. So it is better for your stomach to heat it, right? Okay, so this is the same here that the boiler also to improve its efficiency, then we have to heat the water. So this is at a lower level that the feed water should be heated for the boiler because this will improve the efficiency. This is one issue. The second here is that you look at QH. Now this is here, and instead of this will go to the boiler before it will go at 4 or 5. Now we are going to heat it to 7. Means that when we heat it here, instead of 5, it will be 7. Means that the heat addition in the boiler will be from 7 to 1, not 5 to 1. So the second level here is that we reduce the heat addition. Now the water is heated now. What does this mean heated before go to the boiler? Means that the heat added in the boiler, which is QH, will be less. And therefore, it is expected that the efficiency will be more. So this is the second level of understanding. First, that similarity with the sandwich, then the generator will be happy to have the water heated. The second level of understanding is that when we add, when we heat the water, it goes to the boiler at a higher temperature, and therefore the heat added in the boiler will be less. Then the third level, which Faisal mentioned, is that when we have the temperature higher here, he says the irreversibility will be less and the exergy will be reserved here. So this is what I'm going to give with this figure here. To explain Faisal input, I'm saying that this is the water going in from 7 to 1, and we have gases here going in this direction here. So the gases, we have fuel and air, comes here, burn, and then leave as gases. The heat out of that will go to the water. If I go here back again to this one, you can see from this here that we have gases, fuel, and air here, and this, all of this is hot gases. Then it goes to the tube here. The tube takes the heat and then go to the turbine after that. So what happened here is that we have, okay, I have it explained here. Okay. So I have this here that the gases will go here. So let us look at this here, temperature and entropy or surface. So this is the gases here. These are the gases. The gases go in here and leave out as cold. The water goes in this direction here, and then the heat transferred from the gases to the steam. Now in this case here, the water goes at this point. If I heat it here, means that the difference in temperature is less. Temperature difference is less, means the irreversibility is less, means the exergy is more. This is what Faisal mentioned here. So in the highest level of explanation here, it is that the fact that when you heat this, it goes to, instead of going into the boiler at this point, it goes at this point. Means that the temperature difference here is less now. When you have temperature difference is less, then irreversibility is less, then the exergy is better, and therefore you have improvement in the efficiency. So this is the three levels here of understanding. That, but we, all of them say that the efficiency of the boiler or the efficiency of the plant will be improved. That will explain, that's just the objective here and how we achieve. The objective here is to improve the efficiency. How we improve the efficiency is to heat the water before it goes to the boiler. Why it increase the efficiency? As we mentioned here, that we increase the temperature into the boiler, and accordingly QN will be less here. And this, of course, will tend to increase the efficiency. And also, we explain this with the second law, but by the fact that the temperature difference is less, and therefore the reversibility is less. Okay, Shabab, did we understand the objective and how we achieve that, and explain why is that? Any questions here? I can repeat this again if you want. Okay. Then where do we get this heat from? So the first point here is that we have feed water for the boiler and we heat it. Where do we get the heat from? The heat we take it from, we extract some of the steam from the middle of the turbine and use it here for heating the water. So the water will come here from the condenser into a pump and then heat it in the feed water. How do we heat this? Through steam, getting steam from the turbine. So my question now is that the turbine work will be less or the same?
Less
Which
work.
turbine?
The
The first
turbine work will
turbine.
be less, right?
Yes.
Because now we have certain amount of mass going in here, and it will not continue. Part of it will go out and the rest will continue. So this is one thing again here that I want to understand here, to simulate the turbine with the human body as well. So I simulated this with a human body. Also, I want to simulate this with a human body. Look at the steam here as the blood in this human body. And when you take some blood of our body, then the strength of our body will be less. Means that the work of the turbine will be less here. This is, we do not go to analysis yet, but it is clear here that if we take some of the steam out, means that the water or the steam will not continue. So as it is, as the water is more here, it gives us work. Now we are taking some of that out, so this is reducing the strength of the turbine. Okay, so I'm presenting the mass here. This bracket here presents the mass. If the mass here is 1, it goes here into the turbine, first turbine as 1. Then we have y here. Y here is the fraction we are taking. So if this is 1 kilogram per second, this will be around zero point 0.2 kilogram per second, and the rest here will be 1 minus y. So 1 minus y will continue in the condenser, pump it here to the feed water, then mix it again with y, then comes here as 1 to the steam generator. Okay. Let me go back to this here again and saying here that this is extracted. I use a word here that the turbine is bleeding. This is in simulation with the human body. The turbine here is bleeding. Bleeding means that actually we are reducing the strength of the turbine. We are reducing the work, and therefore I call it bleeding here. And therefore, I want you to imagine what would be the value for Y. Can it be 100%, 50%, or what? Is there a limit for Y or not?
Yes.
I think
Can
it's
you give
small.
me, can you give me a value? I mentioned the word bleeding.
50%,
Yeah, percent. Yeah,
Yeah,
10%.
15% or 20%.
20%.
20%. Okay, if it is 50%, what happens to the turbine?
This power will produce this power.
It will be, yeah, it will
Yes, sir.
die, right? The turbine will die. If we take the 50% of the blood of the body will be, this he will die. And therefore means that you are destroying the turbine here, and therefore you will be fired from your work. For a physician, yeah, and I don't know what they do with him if he take 50% of the blood. So I'm calling bleeding here, such that Y in any solution of your problem should be around 16, 20, 25, something like that. But if we get Y here, 50%, what should I do? Before we start any analysis here. Okay, this is just from simulation of the body. They call it extracted steam, but normally I call it bled steam, bleeding. So this process is bleeding. Why bleeding? Because this is, you are killing the turbine here. And therefore, we can take only certain amount, which is about 20%, as you mentioned. All right, so now I explained what is the objective of the regenerative cycle. This is one issue I wanted to say here. It's very important to know what's the objective of that. And then the second here is how does it improve the efficiency? We mentioned three levels, three scales of understanding. One of them is the food we eat. Second is we are reducing the heat addition, and third is the reversibility from second law of thermodynamics. Then we talked about the turbine, where we get this heat from in the feed water, and therefore we extract it from the turbine, and this bleeding. And if this is a mass 1, this is y, it's 1 minus y. So this will be around 20%. Now this is the first thing we understand. The second thing is that how can we present this on the TS diagram? So let us start from here. This is 1 here. This is state 1. It is in the turbine state 1 here. It goes to the first, we call this high pressure turbine. In the high pressure turbine, this goes from 1 to 2. So we have the mass here is 1. From 1 to 2, the mass is 1.
انقطع الصوت يا دكتور. دكتور.
دكتور الصوت قطع.
شباب is that better؟
Yes.
Yes.
طيب
الحين
الحمد لله.
نسمعك يا دكتور.
So you can hear me, but where did I stop? Where you started not to hear me?
اليوم بدأت تشرح التي اس
Okay.
بوينتو
خلاص.
أنا بوينتو.
Okay, it's closed now. Okay, so now you can hear me, right?
Yes.
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 Okay. Okay. So that's the first thing that you should learn is what is the objective of the cycle. Then how do we improve the efficiency and explain why we improve the efficiency. Then we understand this fully. What happens here, we understand this diagram fully. The second thing that you should learn is how do you plot the TS diagram. State 1 is here. This is P1 and T1. Then the steam goes to the first turbine from 1 to 2. Then we extract some of this here, so part of this steam will go to from 2 to 6. Then at state 2, the remaining of that will go into the condenser and then condense it to state 4. Normally state 4 is saturated liquid. At this point, uh, we pump this to the same level of this here. Remember that this is at the pressure intermediate here, pressure 2. I cannot mix this with state 4. I have to add pressure to that such that all of them will be at the same pressure. So pressurize this to state 5 to the same pressure of 2, and then at 5 and 2, they are mixed together to give us 6. So mix 5, this goes here, and then 2 is cooled. So mix this here, both of them to come at 6. Then from 6, we pump them again to state 7. So there's a pumping here to state 7, and then 7 goes to the boiler to state 1, and the cycle continues. So now from 1, expands in the high pressure turbine. At this part here, there's two divisions here. There's a division here. One division, one part here will go to cooling, to heating the feed water, and the rest will go to the condenser. As you mentioned here, about 20% will go in here, 80% will go in this direction. The 80% will go into the second turbine, then condense it to state 4, then pump it 5, then mix it with this stream here to 6. Then normally 6 is also saturated liquid. Then it is pumped to 7, then go to the boiler and so on. Is that clear, Shabab?
Yes, doctor.
Okay. So now we should be able to understand the steam flow diagram, the TS diagram. Then we go to the analysis. Let me see here. It says here, regenerative feed water heating increases the average temperature of heat addition. So this is why we say that the efficiency has improved, because the average temperature, instead of from 5 to 1, now it is from 7 to 1. So the average temperature we add heat to it has increased. So this is with simulating Carnot cycle, TH has increased, and therefore the efficiency has improved. And the second law of the analysis also tells us here that the efficiency will be improved. All right. So this is here we say open, remember this word here, open feed water heat. When we mix both of them here, this is called open feed water heat. We have another type, closed feed water heater. We'll talk about this later on. Okay. So now let us go here. This is the cycle. Okay, these are the parts for the cycle now. And we assume here, of course, that the feed water here works as adiabatic. But so and this will help us in the analysis. And now let us go again here. It explains the cycle here. How does it go? Okay, now let me just go slowly a little bit. Okay. So this is in the boiler, goes from 7 to 1, as we mentioned. So this is the process here from 7 to 1 on the test diagram. then it enters the turbine, and then take Y out of that. So this is here the process outcome. Remember that we are in the previous cases we say the mass flow rate here. In this case here, because there's a division in the mass, and therefore we will assume that the mass here is 1. And we'll solve it as 1 y and 1 minus y. So this is 1.2.8. And then at the end, if we want to calculate the actual work or the mass flow rate, so multiply by the mass at this point. So suppose the mass at 10 here is giving in the problem 10 kilogram per second. Solve the problem as if this is 1, and this is y, and this 1 minus y. Then at the end, you can get any mass by multiplying by the mass flow rate at this point. So now we have the division here. So this is y. We take y at this point, and then 1 minus y will continue in the condenser, and then comes here to the open type feed water heater. Then we mix them together. So these are mixed together, and then they move again. So this is now 1, and then 1 will go into the boiler again. All right, Shabab? I think the animation is okay here. Shabab,
Yes, it's clear.
Yes,
it's
clear.
clear? Okay.
Yes.
So now with understanding this, we want to go to the analysis here. All right. Okay. Now let us first consider how to get the value for y. The value for y is that how do we get this here? We make the analysis for this here. So let us do the analysis here. So I say that y multiplied by h2 plus 1 minus y multiplied by h5 will give us 1 here multiplied by h6. Let us do this analysis again. Remember here sigma mihi, sigma mihi will be equal to sigma mihi because we are assuming this is adiabatic. Sigma mihi is y multiplied by h2 plus 1 minus y multiplied by h5 will be equal to 1 multiplied by h6. Okay, you understand this analysis here. This is, gives the value for y. So now y multiplied by h2 plus 1 minus y multiplied by h5 will be equal to 1 multiplied by h6, and this will give us the value for y here. Before we solve anything, I'm going to give a problem soon, but y here should be around 0.2 or something like that. Okay, so this is what we call here the mass fraction that's extracted or bled from the turbine. Then once we get the value for y, we want to calculate the turbine work. How do we calculate the turbine work? It is, now we remember that we use the mass here. So now we see here, the mass here in the first turbine. What is the work of the first turbine? I have the mass is 1 multiplied by h1 minus h2. So 1 multiplied by h1 minus h2 plus the second turbine. The mass in second turbine is 1 minus y multiplied by H2 minus H3. This is the work per unit mass at this point because we consider this one. So all of our calculations here will be per kilogram of steam leaving the boiler. Okay, so now we have this here. We have two turbines here. H1 minus H2 multiplied by the mass is 1. Then the left here mass is 1 minus y multiplied by H2 minus H3. I can solve this with another way. I can say here that sigma mihi minus sigma mihe. So I can say here 1 h1 minus y h2 minus 1 minus y h3. This also will give me this analysis. So either you consider one turbine and say that sigma mn minus sigma m exit hx, or you divide it to two turbines and you do this with that. Anyway, you will get here W turbine is equal to that. Then for the pump, we have two pumps. One pump it goes from 4 to 5, and another pump it goes from 6 to 7. The mass here is 1 minus y. The mass here is 6 minus 7. So now I see here that for this pump, 1, the mass here is 1, H7 minus H6, plus 1 minus y, H5 minus H4. So your third responsibility is how to analyze to get W turbine, W pump, and QH. Is it clear? W turbine and W pump. Clear, Shabab?
Yes, doctor.
Okay. Then I'll go to the next step here for Qn. What's Qn now? It is H1 minus H7. So this is Qn. All of them per unit mass here. After I solve this here, please, I'm asking you, all the students here, do not insert the mass in anywhere here. He gives the mass 100 kilogram per second. Forget it. Don't look at it. Solve as per kilogram here. At the end here, you want to calculate the power, net power. Then you calculate W turbine minus W pump and then multiply by the mass flow rate given here. So do not introduce the mass in the middle stages here. Solve as this here per kilogram. Then at the end, multiply by the mass here if you are asked to calculate in megawatt. But all of this here will give you work per kilogram here. W pump per kilogram at this point. Qn per kilogram at this point here. Okay, so now we have W turbine, W pump. We subtract this, divide by Qn. This will give us the efficiency. And of course here Q out. If I ask you what's Q out, so you say the mass multiplied by delta H here. So it's 1 minus Y H3 minus H4. Once we have done this, then we'll go to the calculate the efficiency, either 1 minus Q out over QH or W turbine minus W pump over QH. Now let us take an example. Let me just look at the watch here. It is 9:40, so I'll give this in about 5 minutes or so. So this is one example here that we have. This is a steam power plant here, or this is a regeneration cycle, and therefore we have this is the point. Just the points have been numbering here is different. So this is 5 to 6 here. At 6 we take y, and this is 1 minus y, and then we mix them again and continue here. So this is when you go to the table. So the ideal regenerative steam, and this is goes into the turbine at. So it's giving us this, at this point here at the inlet to the turbine, giving us the pressure and temperature, and the exhaust here at this pressure at the condenser is 10 kilopascal, and then it's giving us the pressure at this point here. So we go to the table at state 5. We calculate the properties at state 5. We get at 3,500. We get the ensembles. We get also state 6 and we get state 7. So we go here and calculate this, of course, with the help of the entropy. So we can calculate these values. Remember here that these values here around the turbine here is all of them is around 2,000, 3,000 or so. Then we'll go to the liquid part 1, 2, 3, and 4, and we calculate this here 1, 2, 3, 4, and then we find here that the insult is given here as HF 191643, and this one. I just wanted to go back here to this diagram and explain, no, to this one here. Just explain one thing quickly here. Okay, with this diagram here. This is, I want to, before starting calculation of the, I wanted to ask to tell you here that when you calculate 1, 2, and 3, all of this is around more than 2,000. When you go to this part, all of this will be less than 1,000, around 1,000 or less. So remember that when you calculate this, and so this is 3 digits here, 191, 700, 900 or so. But this is here 4 digits, 2,000, 4,000, and so on. So remember that in this side, we get around 2,000 to 3,000. In this side, we get from in hundreds. The values are in hundreds. So let me go back to the problem. So make sure that you get this here. If you have a problem here, if you have an error, then this is not correct. So this is here in the liquid part. You see here, this is 191,640, and one says this is 1, 2, and 3, and 4. So these are the values here. For the other side, for the superheated, you can see this is 3,000, 2,000, and so on. So we'll get this from the tables. Then we'll go and calculate for pump 1. Pump 1, W pump 1 is V multiplied by delta P. P2 minus P1 multiplied by V. And remember, this is the value here, 0.5. Remember this, I think was Yazid and Faisal probably remember that W pump is small. Then we get H2 from that, so we can calculate H2 is equal to W pump plus H1, so we calculate H2. This is the way we do it. So we go and calculate H1 from the table as HF. Then we add V1 plus P delta P, so we get this here H2. From that, we go here and calculate y here. So we get y, and then y you see here is 0.16. Remember, I'm just warning you now. If you get this 0.9, means that you are killing a person. If you are a physician, you are killing a person. And now you can suggest what should I do as an instructor here. When you give me this 0.9, what should I do? Can you suggest something?
At least try it. It
Try
should
to
not
not.
be
Yes, very good. Thank you
more
very
than
much. Rod.
50.
So if you get this 0.9, all of us do mistakes. So that is impossible. Just the word is, but living like that, then it is very dangerous here. Okay, so now we get y, and remember this here. I'm telling you now what's the value here. You should not put it zero point 0.5. You should not put it -1, more than 100%. It's not correct. Then you go to pump 2, do the same here. V3, you get this from the table, and then multiply by P4 minus P3. And remember, Faisal and Yazid again, that this is very small here, 2.7. So the previous one, the power is 0.5. Here, this is 2.7. It's very small, and therefore we can neglect. Then we get H4 by adding H3 to W pump, so we get here H4. From that here, we can calculate W turbine. So W turbine is solving the other way now. Sigma energy in H5 minus y multiplied by H6 minus 1 minus y multiplied by H7. So from this I get W turbine. Remember this is 1000 here. And therefore I can neglect W pump with respect to that. Okay. So now we have W turbine. So now we subtract W pump, and therefore we get W net here is 1055.5. Remember here, compare this with the value for this is W net. Remember this 1055. With the turbine, it is 1058. So they are all the same now. Means that the pump work is negligible. So this is W turbine, this is W net. And therefore, so W pump is not influencing here. If you find that this is different from W turbine, then you have made a mistake in W turbine, in W pump. Then better for me to neglect it. Okay. So then we calculate Qn as H, in this case H5 minus H4, and therefore we calculate Qn, and then we calculate the efficiency. The efficiency is around 37.5. It's not 80%. It's not minus. It's not more than 100%. So this here gives us here how do you calculate an example for the regenerative cycle. All right, Shabab. So now we covered reheat cycle, one modification, and the second is regenerative cycle. Then we will talk about the project later on, that where do you do this extraction? We make it here, and where do we have it at this point? Can we have it earlier, close to 5, or closer to 7? This we'll discuss this in the next class. But I want to make sure that you understand now this, and if you have any questions. So what do you do today?
Solve the example again.
Yeah, solve this example or any example. Go to the textbook, you'll find an example. Take the statement of the problem and try to solve it yourself. If you solve it yourself, then you are well done. And the exams we get is systematic like that. I mean, any exam will give you the properties, will be similar to that. We cannot and innovate something else, because this is the nature of the plant. In the plant, we read this data. This is the data given in the problem, because we read it in the control room. And all what we need from you is to calculate the efficiency and the net power output. And sometimes we ask you calculate the mass of cooling water here. But this is from thermodynamics 1. Sometimes we do mistakes, and therefore we have to exercise that. Okay, if I do not have any questions, I can take the attendance now before I forget.
Doctor?
Just give me a minute, take attendance, please.
Okay.
Okay, it is done. So you can ask if you have any question or in this class or in anything else. Yes, please.
Some students are asking about the dates and material for quiz 2.
Okay, the material is already covered now. It is regenerative cycle, reheat cycle. This is the simple cycle, reheat and regeneration. So it will come here as one or two problems of these, and this will be the quiz. When I suggest now I'm done with the material. If you study this material now, I can give you the exam tomorrow, but I'll give you some time to solve many problems, and then it will be on the reheat cycle, on regenerative cycle. So quiz 2, let us decide now. Today is so either Thursday or Sunday. It will be on
Thursday.
Thursday
No,
better this time.
يا
Thursday.
شباب I'm not going to leave this for you, all right, please يعني, okay, because I know I'll get divisions here, some of you have quiz and so on, but يعني it will be like that. If you all agree to one day, I don't mind, but if there's a difference, then I have to put my input. All right,
Quizzes in this week, lots of quizzes.
I have no problem. As I told you, I can make it Sunday or Tuesday even. If you all agree to one day, I don't mind. But if you do, normally you do not, so I will put a date, so I can say Sunday unless you wanted another day and you all agree to that. But can we? Okay, I don't. Okay, we can decide now. How about Sundays? Okay.
Yeah, it's okay, Doctor.
Yes.
Yes.
All of you agree to Sundays, so you have a weekend. You can study that.
Yes.
خلاص. We make.
دكتور
Nah.
اذا هو بس انا اللي معترض خلاص يعني.
نعم. Yes.
خلاص Sundays okay.
Sunday والماتيريال وإيش دكتور؟
Material, I already prepared an exam, okay? It will be one problem on regeneration and one problem on reheat cycle. Of course, it will take too long, but I'm doing something there, okay? I'm not asking you to calculate all the enthalpies from the table. I am giving you the things that the enthalpies that take some time from you, all right? So I'm not going to spend a lot from thermodynamics 1. So it's two problems, one regeneration and one reheat, and all standard, similar to the examples I gave here. So it is Sunday, next Sunday we'll have two problems, one regeneration and one reheat. And as you mentioned earlier, it will be around 8 points to 10 points, something like 5 to 10 points. Yeah. And as I told you also, I will try to drop the worst quiz out when we finish. So each chapter will have a quiz. Okay, Shabab, so we agreed on Sunday, inshallah, but I just wanted to tell you some part A of the any question will be because I'm relating the mass flow rate or some of the properties or some choice of the problem with your ID number. So please do not make a mistake. Part A will ask you of the result, how to use your ID number, and this will be 2 points. All right, so if you just know your ID number and calculate the mass flow rate, you will take 2 points. All right, I don't want mistake in that. Okay, so we agreed today that will be Sunday.
إن شاء الله.
دكتور طيب الدياجرام اللي هو هذا بيكون معطى لنا ولا احنا نكون حافظين انه كيف تدور الدائره؟
لا sorry, can you ask again please?
اتكلم عن الدياجرام اللي هو الباوند والترباين بتكون معطى لنا الصوره ذيك الدياجرام
Total steam في steam flow diagram و TS diagram. The steam flow diagram I will give you that.
Okay, that's
The steam flow diagram will be given, but the TS diagram most likely I will ask you to do it. Okay.
دكتور هل السيلبس تغير ولا لا؟ لأن في